Good morning. So yesterday we proved Schur's lemma. What does it state? If I have D on B and D prime on V prime are two irreducible representations of G, and T is a map from V to V prime such that T dg is D prime G T. If T is defined in this way, then we say that T intertwines these two irreducible representations. For all G. Then what can we say about T? T can be 0, which implies D, D prime are inequivalent. T is non-zero. T is non-singular. D, D prime are equivalent. And T singular such a possibility never arises if T is defined in this fashion. So this is Schur's lemma. We proved yesterday if D is equal to D prime, V is equal to V prime, and T dg is equal to dg T, then T is multiple of an identity. Now let me define mean of some function. Let me define mean of some function as 1 over order of the group into sum over all group elements, the value of the function. That means if I have some function from G, so some function defined for each of the element, so this I will define it as mean. This is just or I simply don't write it. This is simply mean of f. Mean of f. So I am just calling it f. G is order of the group. So this is order of the group. Yeah, it could be actually one of these D's. Okay, so it's any map. Now I am going to define for an arbitrary S going from V to V prime. Okay, so okay, let me write down for an arbitrary S from V to V prime, define Ts as mean over G of d prime of G inverse into S into d of G. D is a irreducible representation, D prime is an irreducible representation. So I am going to construct a map like this. Now supposing if you operate this on an element of X, element of V, D into element of V will become, so ask what happens if Ts is operated on X for some X in V. Ts of X operated on X. So dg operating on X will give an element in V only. S operating on X will give you an element in V prime. D prime operating on that will give an element in V prime. So Tg of X is in V prime. So first notice that this Ts is a map from V to V prime. Okay, this Ts, the way I define, is a map from T to T prime. Now consider d prime of G prime inverse into Ts, d prime of G prime inverse into Ts for some G prime inverse in G. So what can I write about this? D prime of G prime inverse into Ts is equal to mean of, so I take this inside, then I will have d prime of G prime inverse into d prime of G inverse into S into d of G, correct? I am just considering this. You will realize why I am considering this in a minute. So d prime of G prime inverse into Ts is, I will take d prime of G prime inverse inside. So this can be written as, from the definition of representation, this is nothing but d prime of G prime inverse into G inverse, correct? Because this preserves the group multiplication table, d of G. Now what we can do, another element in the group, okay? Now I can say G prime inverse G inverse, I will call it as some G double prime inverse, relabeling it, because closure is there, I can call that element as G double. Now what this G double prime will be? G inverse, so G prime, correct? G inverse of this is inverse of this, that is G prime, correct? So what G will be? G will be G double prime G inverse, sorry, G prime inverse. G is G double prime G prime inverse. Okay, the actually the operations are you will realize why I am doing all this. So I am going to put this circled ones for these arguments. Here I am going to put G double prime, here I am going to put G double prime G prime inverse, and the mean is over all the group elements. So this G is dummy, instead of G I can put G double prime. So this will be equal to mean over G double prime d prime of G double prime inverse S and d of G double prime G prime inverse. Okay. Now this can be written as over G double prime d prime of G double prime inverse S. Again I use the group property representation definition, this into d of G prime inverse. Now what is this? That is the TS that I have defined. So I have now, this is equal to TS into d of G prime inverse. So I started with an arbitrary G prime inverse and I showed that TS into d G prime inverse is equal to d prime G prime inverse into TS. So what did I show now? I showed that a map from V to V prime defined in this fashion using the two irreducible representations intertwines this. In Schur's lemma, I have considered a map that intertwines. Here I have constructed an intertwining map. Correct? So this map TS defined in this way intertwines these two irreducible representations. Okay? So we say that TS intertwines D and D prime. Why we want such a map? Because we know if an intertwining map is there, we can use Schur's lemma. Correct? Now what Schur's lemma tells you has to be 0. It has to be 0 for all S. Whatever is your S, it has to be 0 because the S is arbitrary. Correct? So if D and D prime are inequivalent, if D and D prime are inequivalent, Schur's lemma tells you TS has to be equal to 0. For all S, whatever S you take, this is true. Okay. The result is invariant of the choice of S, so I can as well choose this S to be an identity matrix. Then what do I have? I have M of G into D prime of G inverse into D of G is equal to 0. What does it mean? It means this is equal to, this implies 1 over order of the group sum over all the group elements D prime of G inverse into D of G is equal to 0. That's what since it is true for all S, I will take S as identity. d prime of G inverse into d of G is equal to 0. Now what does this mean? This is a matrix and this is a matrix, correct? These are matrices. So how do I write this one if I want to write it in terms of the matrix elements? Okay. So let us say, without any loss of generality, let d prime are unitary irreducible representations. If they are unitary irreducible representations, then what will happen? You can say that 1 over G product over so sum over all the group elements G, d prime of jk of G, which means it is jkth element of this matrix, it's a star, and d of Lm of G, d of Lm of G is equal to delta is equal to 0. If d and d prime are inequivalent, this is all the time equal to 0. Okay, so what essentially I am trying to tell you is that if I take any jk element over this group, that will be equal to 0. So it will be a 0 matrix on the right hand side. Okay. Now what happens if they are equivalent? What can we say about Ts if they are equivalent? Let's say d is equivalent, d is same as d prime. Ts is invertible in general, but there is also a stronger result. Yeah, non-singular, but we have also shown if d is same as d prime, identity. So d prime are equivalent, then Ts is lambda of S times the identity. Of course, this lambda will depend upon what is the choice of S. Now we can write down a relation of this type. So let d of alpha and d of beta be two irreducible representations. Okay, so let's say two UIRs, unitary irreducible representations. Okay, then we can define on L2 of G, this is space of square summable functions, space of square summable functions. What will be the dimension? This is a vector space. What will be the dimension of this vector space? Dimension of this vector space is order of the group, because we will have as many group elements are there, so many components will be there in this vector space. You can define an inner product on this vector space F1 F2 as F1 star F2, F1 star F2. If I have two functions, one is F1, other is F2, I can write down F1 okay, maybe let me put it this way, f and g. So I can write down fi star gi sum over I is equal to 1 to order of the group. Such an inner product I can define. Now these results actually imply the following equation: T of alpha jk okay, comma